We have seen a lot of complexity measures till now. You can clearly see some of them were related. We defined degree. What was degree? How would you tell someone what is the degree of a Boolean function f in terms of its Fourier representation?
No, I mean highest modulus non-zero Fourier coefficient. That
Correct.
modulus is it?
The size maximum over the size of the set, right? Whose Fourier coefficient is non-zero.
Yes.
Correct. That is the Fourier degree. And what was the approximate degree? Anyone else except Udit?
The minimum degree of the polynomial approximate.
Very nice. The minimum degree which approximates f. And when we talk about approximate degree in this area, in this literature, generally that approximation is the L infinity approximation. That means the polynomial should approximate f at every point. This should be less than equal to epsilon. And then we find the best possible degree or minimum degree of a P which approximates f. Then we saw deterministic tree complexity, or we can call it deterministic query complexity, where we were allowed to query any index of the input, and we were charged according to how many queries we did. The simplest model was deterministic tree, where we had a nice tree, but then the things can become complicated when we're allowed a distribution over the deterministic trees, or we are allowed to query randomly. Both were similar. This was called the randomized tree complexity. And then we also saw the variant where the queries could be quantum, the algorithm could be quantum. Since we did not have background in quantum, we didn't go into it deeply. But what we saw was that some sort of polynomial method can give us a lower bound on this quantum query complexity. So we have seen many complexity measures. We have not tried to relate them till now. They come from different avenues, right? Degree comes from algebraic domain. This deterministic query complexity is very much a computational thing. And in defining all of this, the intuition was, oh, if there is a hard function, then the complexity measure should be high. If the function is easy, then the complexity measure should be low. If the function is difficult or complicated, complexity measure is high. If it is easy to compute, to represent, whatever, then the complexity measure should be low. Intuitively, that means we should say that if complexity measure 1 is high, then the other complexity measure should be high. If degree is high, then approximate degree should be high. If deterministic query complexity is high, then approximate degree should be high. The intuition is correct, but life is not fair, and it can happen that these quantities are not exactly equal. And in some sense, this is one of the fundamental problems in this area to kind of relate these complexity measures. Can it happen that degree is very high, but the approximate degree is very small? Can it happen that the quantum query complexity is very high, but the approximate degree is very small? Or the other way? These are the kind of things we want to look at in the next 2 weeks. And it turns out that the first order of work is to introduce some more complexity measures. What we will do is increase this jungle of complexity measures, and then the relations between them will pop out. And these new complexity measures are very inspired from deterministic query complexity. When you want to study deterministic query complexity, if you are a mathematician or a combinatorialist and you want to study deterministic query complexity, then in some sense, these measures come out naturally. You will see the measures, we will get a hang of it, we will practice it, and then we will see the relations between them. So let's get ready. Let's look at what new measures do we need to define. First important thing to remember now is that for the following 2 weeks, we will assume f to be a total function. In case of partial functions, things can go awry. They can become very, very awkward or weird. So we assume f to be total. What does it mean that f is total?
Defined on the entire
Great. It's not a partial function or a promise problem. That means it is defined on all the input values. My domain is the complete Boolean hypercube. This is something I will assume throughout this lecture. Now, knowing this, let me start with the first complexity measure called sensitivity. How many people know what sensitivity is? Just raise your hands. Okay. So then let's take it slightly slowly. What is sensitivity? You remember we defined, given an input x, we defined a notation x XOR I. Do people remember what this is? Again, I would say except Udit, because I think Udit knows this well. What is this input?
Flipping the I.
Correct. Flipping the ith bit. And this was actually very important. One of the important questions which we asked were, is fx equal to fx plus I? This gives us the definition of sensitive bit or sensitive index. I is sensitive for x if and only if f of x is not equal to f of x plus I. So an index is sensitive for an input if, when you flip that input, the function value changes. Can you come up with an x and an f where every bit is sensitive?
Parity and any input.
Okay, very good. If you take parity and any input, then you know that since as soon as I flip something, the number of ones will become odd to even or even to odd. So actually parity is sensitive on every bit and every input. Anything else except parity? I think someone else wanted to say something. Any other example? Any function which has just one input where it is sensitive on all n bits. Or okay, let me change the question. Let me make it this way. Give me a function.
Majority can be considered when we are at the just at the middle.
No, but it will only be sensitive on at most half the bits, right?
Any which has different values on the neighboring part or neighboring Hamming weights, but then that would be a parity.
So if you wanted it to be n for every input, then yeah, so you have kind of given a proof that how should we say it? What you have proved is that if for every input n, every input x, every bit is sensitive, then your function should be parity or minus of parity. That is correct.
I only did this for a symmetric case.
But you don't have to use the symmetric. You start with an x, right? Whatever is the function value, the level below it, there will be n connections. So you can kind of argue that what you can do is there will always be a path between x and y, right? Which will be so whatever is the Hamming distance between them, if that is even, then the value should be minus of that. So the value should be same as f. If the parity is different, sorry, if the Hamming distance is odd, then the function value should be different, right? If everything has so okay, so let me just ask, is it clear to people what statement am I proving? I'm proving that if every input has all the bits sensitive, then my function should be either parity or negative of parity. How many people agree with that? Okay, so you don't see the proof of this?
Can you repeat just once again what you gave the proof?
Yeah, the statement is, if we know that every input x and every I is sensitive for every input x, then my function f should either be parity or negative of parity.
Yeah, that is the statement. What's the proof?
What's the proof? Okay, so let us
Can
start
we
with
say that if we just fix the value of one particular input, then
correct.
from that we can go out to all the inputs and find their values just by changing one bit and like doing all the things.
Exactly, that is the proof. If you look at x and
Got it.
look at y, right? If the Hamming distance between x and y is odd, then there are odd steps, right? And since it is sensitive, the value should change odd number of times. That means fx is not equal to fy. If the Hamming distance is even, then the function value will change even number of times. That means f of x is equal to f of y. Right? In the Boolean hypercube, between any two vertices, there is a path. And what you know by your statement is that your function values should change on every edge of the path. Does this make it clear?
Yeah.
Okay. So yeah, anyway, so what I was asking was, let's ask a different question. Can you give me a function and an input where no bit is sensitive? Is it possible?
Constant.
And function, yeah, constant function,
non-constant function then?
and function, and
Very good.
any
All
input
zeros, right?
yeah.
All zeros.
Any
Now
input
we
except 1111. Yeah.
that is not correct.
Oh
If
yeah,
I have
yeah,
n minus 1 ones, then
yeah. So at most n-2 ones.
correct, right? So all those cases can happen, right? And then by this argument, the sensitivity of x, sensitivity of an input, what should it be? What is your guess?
Number of positions which
Number of sensitive bits, right? That's kind of a natural thing to define. So we see that s of f comma x could be sometimes 0, could be sometimes n, it could be anything, but it will obviously be between 0 and n. Right? So how many x's are there for which the sensitivity is strictly more than 1 in OR? For the OR function. How many inputs are there for which the sensitivity is more than 1, strictly more than 1? I think sensitivity is at least 2.
Just one input.
There is just one
All
input.
zeros.
All zeros, right? For inputs which have just 1, the sensitivity is
1.
1. And if it is more than 1 ones, then the sensitivity is
Hamming weight.
sorry,
Zero.
Hamming weight.
not Hamming weight, it is 0. sensitivity is 0. For the OR function, if I take the input 0, 1, 1, 0, 0, 0, there is no bit which can be flipped and the function value can be changed. So the sensitivity of this input at OR is 0. Right? This should be clear to you. And once you have defined the sensitivity at an input, you can define sensitivity of a function, which is maximum over x, s of f comma x. Notice this pattern. This is the way in which we will define many of the complexity measures. Finally, sorry, this is sensitivity of the function. Generally, we talk about sensitivity of the function. That is what I mean when I say complexity measure of the function. This is this final sensitivity. Right? So the sensitivity of OR is
and
parity,
and
good. Addressing, let's say addressing on k. That means the input size is k plus 2 to the power k.
K.
Almost correct.
Okay, k plus 1.
K plus 1. And you have to be careful, right? You have to create an input so that on every Hamming distance 1 index, the bit written is different, right? So you have to create that x carefully. Right? Where this sensitivity would be k plus 1. But there is an input where the sensitivity would be k plus 1. So sensitivity of addressing is k plus 1.
how can we say that it can't be more than k plus 1?
It can't be k plus 1 because whatever is your address, right? Except that all the target bits you can flip and nothing will change. So
Okay.
what is addressing? Your address and your target, right?
Oh, yeah, the address and the target bit, if those are fixed, then value won't change.
Then the value won't change. Okay. Now, another thing, just to relate it with whatever we have learned, we can define average sensitivity. So average sensitivity of f is 1 by 2 to the power n summation over x s of f comma x. Okay. Is the definition of this thing clear? Questions about the definition? Okay. If there are no questions about the definition, actually this thing is equal to one quantity which you have studied before. Can you guess which quantity? And the hint is, where did we care about this kind of thing?
Influence.
Yes, exactly. So this is going to be equal to influence. How many people can prove it? I will give you 2 minutes to think about it. Any ideas about how to prove that this is influence?
Can I say?
Yeah. Udit, you wait. That other things. You have slight advantage in proving these things. So
Because when we were talking about total influence, then we were summing over all the bits. I mean, over all the influences. So now, whenever we talk about S, F of S, F and X, S of F of X, then if if those I bits are sensitive, then they will be counted in that corresponding influence.
Good. So you have got the idea. If you remember, what was the influence? It was the sum of the ith influence. This is ith influence, right? Number of inputs with, obviously normalized number of inputs where fx is not equal to f of x plus. What about average sensitivity? 1 by 2 to the power n summation over x s f of x. What is s f of x? Summation over I.
One f of x is not equal to x XOR I.
Exactly, the indicator that f of x is not f of x plus I. In one, you summed up over x first, and then you summed up over I. That was influence. In case of average sensitivity, you summed up over I first, and then in the end, you summed up over all the inputs. But obviously, these two summations are one way to see why sensitivity in itself is an important concept. It relates with the influence of the function. Is this sufficient enough proof, or do people need clarification? It's just exchange of summation. Okay. So if this is clear, let's move forward. Let's talk about the next concept, which is called the block sensitivity. It's very, very similar to sensitivity. We are in some sense generalizing the concept of sensitivity. A block B, so a block means a block of indices. It need not be contiguous. It's any subset of n. When would we say that a subset of block, a subset of n, a subset of indices, a block B is sensitive? When should we say it is sensitive? What is your guess?
Flipping all of the bits in D will change the value of the function.
Correct. And we will denote it by xb, right? Or x XOR b, whatever, right? If we switch everything in B, the value should switch. That is the definition of a block being sensitive. What should be the block sensitivity of an input on function f, or of a function f at input x?
Number of blocks.
Number of blocks. So that means block sensitivity can go up to 2 to the power n, correct?
Yes.
Yeah, but we want it to be between 0 and n, right? In some sense, that that thing is trouble when you can you can change it from 1 to the power n. So could we put a restriction so that it remains between 0 and n? We will put the additional condition that the block should be disjoint. So there can be many arrangements, many set of disjoint blocks, each of which are sensitive. The block sensitivity is the maximum number of disjoint blocks which are sensitive. Okay, so B2, BT, each of them should be sensitive. Each of them should be disjoint. BI intersection BJ is phi. And f of x is not equal to f of xbi. If that happens, we call it to be like a valid block sensitivity blocks, and the maximum number of disjoint blocks we can collect, those are called, that is called the block sensitivity of an input at F. And what should be the block sensitivity of F? That should be easy. That's like sensitivity. It is
Maximum of BS fx over all x.
yes. Right. So what can you trivially say about block sensitivity and sensitivity?
Block sensitivity is high
Why?
because even the one, when you consider, if you just take single blocks.
If in
Single
some
blocks.
input, let's say there are some bits which are not sensitive, but together they become sensitive. So
Right.
that could increase the number of.
Right.
So
That
that
is
could increase BS fx.
correct. But at least one arrangement we know, which will give us sensitive number of sensitive blocks. Right. So one arrangement where we only take singleton subsets, singleton blocks, that will give us at least sensitivity. Now it can happen that you take a block of 2 and you might get better. That we don't know. But at least whatever block structure is possible for sensitivity, same block structure is allowed for block sensitivity. There can be more blocks. Right? Though there can be more block structures. So this should be clear from the definition. And since this is max over x, that means BS of F is greater than sensitivity of F. Let's see how we can understand it more. So all of you saw that block sensitivity of F at x should be greater than equal to S of F at x. Is there any question about this? Does everyone agree that this is correct? Any questions? Okay, so I assume this was quite clear. This was just by taking the blocks to be of size 1. Now give me a pair of inputs such that block sensitivity is strictly bigger than the sensitivity. Is that possible? Or is it that block sensitivity is always equal to sensitivity?
When we were considering or
Okay.
then, for inputs with Hamming weight greater than 2.
Input with Hamming weight?
Greater than 2.
Hamming weight bigger than 2. Okay.
For that, block sensitivity would be, greater than 2, but the sensitivity would be 0.
In -1 it should be. Like,
Sorry?
so we can make the box sensitivity to be n-1 in this case, like when there are 2 ones and all the zeros.
Okay, good. Now, let me put it this way. Now, I want sensitivity to be non-zero. And can you still create a function such that this happens? So I want a function and an x such that S of F comma x is greater than 0. But still, this inequality is this inequality is strict. Any ideas? Okay, so we will see this. We will try to create these. But okay, we can see that it is strict. We will go ahead now. Now, obviously, we don't care about block sensitivity of f at a particular input, right? As I said, complexity measure is defined just for a function and not for an input. So can you create a function where block sensitivity is more than sensitivity? Obviously, this is true, right? Block sensitivity is always greater than equal to sensitivity of f. This just follows from here. But can this be strict? This is a much tougher question, right? Because for the example which you gave us, or the sensitivity and block sensitivity both were
In
right.
For majority, it might be.
Okay. Okay. So what input of for majority? What is the sensitivity?
So if my input is in between, then so so like half of the bits would be like sensitive bits.
Okay. So n by 2, right?
Yes.
What is the block sensitivity? Can you get any input where block sensitivity is higher than n by 2? No, right?
No, I guess because it is monotone.
So block sensitivity is also n by 2. Okay, but let me put it this way. This is a hard question. This is not an easy question to answer. It's difficult to come with a function. And actually, if you think about symmetric functions, you might be able to differentiate between sensitivity and block sensitivity by a constant factor. But obviously, we want asymptotic differences, right? It's not good enough that we have only, how should I say it? Only linear differences like n by 2, 3, n by 4. This is not good. We want block sensitivity and sensitivity to be away in a asymptotic. So let's try to create this. But to create such an example, we need to define another block sensitivity, a block sensitivity on an output. So block sensitivity of a function at an output. So let's say BS0 of f. These are very natural. You will see that it's just a new notation, but the definitions agree with your intuition. So as I said, it is defined for an output 0. So what should be max over?
F inverse 0.
Very good. Right. And similarly, I can define BS1F right? So I can define S1F, BS1F, all these things can be defined. And we will see their use pretty soon. They are not standard quantities, they are only used to prove results. And we want to separate block sensitivity and sensitivity. That's why we have defined this. You don't have to remember their definitions as such. It will just be used to create the separation. But now, can you find a function where this happens? Block sensitivity at Z is more than sensitivity at Z for any Z and for any F. You can pick your function F, you can pick your output Z, but your block sensitivity should be more than sensitivity. This definitely does not happen with OR. What else can you do? Can you modify OR slightly? Can you think of a function where block sensitivity of the output Z is strictly more than sensitivity of Z? Sorry. What about threshold 2 function? Do you know what threshold 2 function is? It should have at least 2 ones. What is the sensitivity of this function? Or let's say S0 of F. See, I'm talking about symmetric functions, and there are actually only two kind of inputs where the function value is 0, right? For this
N
threshold.
minus 1.
Very good, right? These are the only two inputs you should worry about, all zeros or Hamming weight 1 inputs. S1F,
One.
S1F is 1, because if the Hamming weight is more than 3, then the sensitivity is 0. If the Hamming weight is 2, then actually sensitivity is going to be 2. Correct? And you will see that even the block sensitivity is n minus 1. And BS1F is equal to 2. But here, if you saw the block sensitivity of F at all 0 inputs, what was that? What was that?
N by 2.
N by 2, right? So now think of a way to change this function slightly so that we achieve what we wanted. The problem now, what is happening here is the sensitivity becomes big because of this Hamming weight 1 inputs. Can you change your function slightly so that the block sensitivity the function remains almost like this, but the block sensitivity is highest or at all 0 inputs? Can you put a restriction over the function? Can you modify it slightly?
So the function should return 1 only at Hamming weight 2 inputs.
Exactly 2? Exactly 2 Hamming weight.
Yes, exactly 2.
That's called an exact 2 function. What is the sensitivity? It would still be n minus 1, right?
Yeah. Yeah.
So that's not good. Exact is not good.
Yeah, 1 or 2.
So
No. So yeah.
yeah, think outside the box now. Think of non-symmetric functions.
It's the same as threshold 2 function, but for one particular input, let's say 1 and the rest zeros, the value is 1.
Okay. So either the Hamming weight should be 2 or
either the Hamming weight is greater than equal to 2 or the input is 1 followed by all zeros.
No, but then if I take 0, 1, 0, 0, 0, 0, again the sensitivity would be n minus 1, no?
Oh, okay, right.
So I have to destroy this sensitivity somehow, right? This n minus 1 is hurting me.
Only the first two bits should be 1.
Then block sensitivity will be very, very small. That's a nice idea. So you said this, right?
Yes, for this it should be 1.
Correct. That is correct. But then it is hurting me. It is in the sense that block sensitivity is also going to be small.
Consecutive bits should be 1.
Very nice. Very nice. So we reached there, right? So think of a function where only a contiguous block of 2's is 1. Right? So only this input or this input or this input, only these inputs are 1. Otherwise, it is 0. Correct? So what is the sensitivity of this function? So let me just find a new page. So f of x is 1 if and only if a contiguous block of size 2 is all ones. So that means either my input is this or this right? Then what is the sensitivity of this function?
Two.
Very good. What is the block sensitivity of this function at 0, at output 0? I'm sorry.
N by 2.
N by 2, right? So we achieved what we wanted, right? At the output 0, block sensitivity is much more than sensitivity. Though still we haven't achieved a separation between block sensitivity and sensitivity. That is because what is sensitivity of S1 of F?
Again 2.
Are you sure?
N?
Sorry,
N.
how is it N? On what input is it N?
On any input with contiguous, let's say 1, 1, 0 and all zeros.
No, just take all ones, no? Oh, wait, what am I saying? No. Yeah, so, sorry. Yeah, if I take this, then if I change anything,
Each
my
bit is
function will
sensitive.
become, each bit is sensitive. Then this is N. What is BS1 of F?
N because it is greater than equal to S1F.
Yes, and it cannot
Less
be
than equal to
more,
N.
right? So, okay, we achieved our goal partially. We could create difference between block sensitivity Z and SZ, but overall block sensitivity and sensitivity are not different. We still haven't
I did not understand S1 of F.
look at this input, right? This is a 1 input.
Yes.
Change any input bit of this. If you change any input bit of 0, then your Hamming weight is 3. Function value is changed. These are the only inputs on your function is answering 1, right?
Okay, got it. Yeah.
Right.
And
So either once you change any bit, either the Hamming weight will be 1 or 3.
yeah, so
function value will-
automatically BS1 of F is N of N.
Correct. Right. So we have almost achieved what we wanted. We created a difference between BS0 and S0, but still we haven't created a difference between BS and sensitivity. We need one more idea. It's not an easy idea, but I will give you 1 or 2 minutes to think about it. You want to create a separation between BSF and SF using this contiguous block function. What should we do? What is the idea? See, what has happened is our S0 is getting overshadowed by 1 sensitivity. So we want to do something so that our S0 sensitivity or 0 sensitivity becomes the important sensitivity. And S1 and the 1 sensitivity remains. We want to do some operation on F so that suddenly the 0 sensitivity becomes important and 1 sensitivity is small. It remains the same or it doesn't change much. What kind of transformation can we do with F? Okay, is there a function whose 1 sensitivity is very small and 0 sensitivity is very high? Or very good. For or, S1F is, what is S1F?
1
S0F is?
n.
Right. So now, can you think of some idea by which I can use F to create a function where sensitivity and block sensitivity are different?
Some composition of like both the functions or and this function.
Very good. The simple idea is composition of or and F. So let's see what happens when we compose or within any general function F. Is everyone on board? Have I lost anyone? This is all very, very simple, basic, elementary stuff. We just have to be present and keep applying. None of this is difficult, right? So that's why I hope that everyone is trying to follow. None of this requires any background. This is simple high school stuff, which you can try, right? So now we have the function or, we have the function f, and we compose. There are n many things here. Each of them have a copy of f, and f has arity f. Okay. What is the sensitivity of this function? So if this function is 0, that means in every copy of f, if the function value is 0, that means every input of f is giving me value
0.
correct, right? So if my composed function is giving me value 0, by the property of or, each of the inputs of x should be giving me value 0. If I want to change it to 1, that means I can just flip any of the f's to, if I flip any of the f's to 1, the function value becomes
1.
So then what should be the sensitivity of G?
N times like S0 of or would be, this composite function would be n times S0 of f.
You see that, right? This is the best you can get. At every input of f, the max you can change is S0. And there are n such copies. So the maximum you can change is n times S0. And there is a function like that. Take any 0 input of f, and place it here, whose sensitivity is the highest. And then clearly the sensitivity of G is n times sensitivity of f. Questions about this? by a similar argument, you have to kind of put your mind to it. It's not very difficult. You have to show that there is no point in picking a block which is taken from two different inputs of f. That is never going to help you. Okay, and that's actually simple because the value of at least one gate should be changed. So you can assume that each of the block is only picked from one input of f. You can think whenever you define block sensitivity, you have a block bi. We want it to be a minimal block, right? What does it mean that the block is minimal? That means this is the smallest block such that f of x is not equal to f of x bi. If I take any subset of bi, then the function value does not change. Since I'm interested in figuring
Just
out
a second. So for S0G, if we change, let's say, we just need to change at max S0F bits of the first block so that the result of that gets flipped to 1.
No, we don't need to change S0 bits. Any of S0 bits, if we flip, the function value becomes 1.
Oh, okay.
Yeah. So since in the block sensitivity, we are talking about maximum number of disjoint blocks, it makes sense to keep our blocks as small as possible. What does it mean as small as possible? We can keep our blocks to be minimal such that if I change, if there is any subset of bi, the function value does not change. I can assume that these are my blocks, my blocks which give me the maximum block sensitivity, right? They have the smallest size, the disjointness cannot change if I take a further subset. So I should keep my blocks minimal for block sensitivity. And here again, if there is a block which contains variables from two copies of f, at least one of the f's should be changing. So why not restrict just my block to the entries in this part? I'm not going to detail. This is not going to be very complicated. If you think about it, you will see that this is also going to be BS0F. What about S1G? What are the one inputs of G? How many copies of F should be 1?
At least 1.
If there are more than 1 copies of F which are 1, then what happens?
Then
the sensitivity is
doesn't matter. I mean,
then the sensitivity is 0, right? At that input.
yes.
For any input, more than 2 Fs are giving me 1, then there is no way to flip a bit and change the function value to 0. Because at least one of the gates in this level will remain 1. Right? So the only inputs where you have some sensitive bits are the Fs, are the blocks. Each block, there is exactly one block, one F which gives me 1. But if there is exactly one block which gives me 1, there is no point in making other 0 Fs change their value. So then what is S1G?
S1F.
It is just S1. And again, a very similar argument will show that BS1G is also BS1F, though you don't need it actually. If it is higher, see, definitely this is true. Equality is correct, but you don't need it. If the block sensitivity is higher, it's okay. But now you see what we have achieved, right? We have emphasized the role of 0 sensitivity. And we have got the S1 sensitivity down.
So could you repeat S1G once?
Sure. What is a one input for function G? How many copies of F could be 1? At least 1. At
Yes.
least 1 copy of F should be. If 2 copies of F are 1, then my claim is sensitivity is 0. Do you see that?
Yes.
Right? Because if you change any input, at least one of the gates will still remain 1. The function will remain, function will not change its value. So now for considering S1G, I should look at only those inputs where exactly one copy of F is 1. Now, at any other gate, there is no point changing things, right?
And so we have to look only at one of the F. So it's
One of
S1.
them, S1. Yeah.
Okay.
Right. Okay, good. So this a similar argument looking at the minimal blocks, you can show BS1G is equal to BS1F, but it's not useful for us. Now, if I take F to be this contiguous 2 function, right? And if I take M to be equal to N, what is S0G?
Two N.
2N. What is BS0G?
N square by 2.
N square by 2. What is S1 of G?
N minus 1.
N minus 1 or whatever order N. And BS1G is again N minus 1. So now we have created a quadratic difference between block sensitivity and sensitivity. Right? So for F is equal to or times C2. Let's say this is the function. I'm just introducing a new name. Contiguous 2 block. Right? Or 2 ones. If I saw, I'm calling that function C2. And if the additive was equal, then S of F was theta n. Block sensitivity of F was theta n square. So block sensitivity was quadratically bigger than sensitivity. This is the best possible separation known. This kind of function was created by Rubinstein. And we don't know a better separation between block sensitivity and sensitivity. If you can create a function where leave alone constants, if you can show that SF is less than, SF square is less than BSF, you will have a very, very good paper. You will become famous. We don't even know this. Leave alone SF cube. If you show SF cube, that's great. But even showing a function where block sensitivity is greater than SF square, this is open. This is the best possible separation known between sensitivity and block sensitivity. Okay, this is an open problem. Any questions about this? Okay. The last concept we will study will be of a certificate. A subset n for x, for an input x, is called a certificate. If fixing yi to be equal to xi for all I elements of S implies f of y is equal to f of x. So think of this name, English meaning of certificate. It is a subset of x such that if I know the value of that subset, if it is equal to xi for that input, then I know that the function value is fixed. For example, for this, knowing that the second bit is 1 is a certificate for OR. Okay. What is the certificate for all zeros for OR? What is the smallest possible certificate?
in the entire set.
N. Right. Right. So the certificate complexity of F is the sorry. This is the size, the minimum size of a certificate for Sx. Okay, you are looking for the minimum possible certificate size, certificate for X over F. Is the concept of certificate clear? If you fix those input bits according to X, then you know the function. That's called a certificate. And the certificate of F, complexity of F, is again max over X, C F comma X. Like block sensitivity, we define C of F. Right? So the only thing to notice here is that generally for block sensitivity, we had some kind of a max here, max number of.
So basically, we are saying that restricting the function, if S is a certificate, then restricting the function on the indices of S according to X will
Right. The function
give
will
us
become
a
constant.
constant.
Very good. Very good.
Okay.
Yes. And you have seen it somewhere else also, these certificates. You have seen it in deterministic tree. Where do you get certificates for deterministic tree?
Computation paths?
Yes. Every computational path is a certificate, right? Because at the end of the computational path, you are giving 1. What does it mean? That you know now, knowing just the values at this computational path, at these queries, you know that the function value is 1, right? So this a computational path is actually a certificate for function. Each of the computational path in a deterministic tree is a certificate for inputs which lie on those leaves. There are a lot of inputs which lie in these leaves. For each of these leaves, this computational path is a certificate. Right? Do you agree with that? What does it tell us? What does it tell us? The relation between DF and CF?
Equal.
No.
CF is at least DF.
There were 3 relations possible. You have given all the incorrect answers. DF is at least CF, right? Because remember, any deterministic tree, that you look at the depth, you have a certificate there, right? But then you could have a minimum, you could have a better certificate. You have a minimum here. You could have had a better certificate. You didn't use it. But at least whatever is the depth, it is more than the certificate complexity. Right? Look at the deterministic tree. Look at the path where this X is achieved, right? That is a certificate for X. And since we have minimized over all certificates for X, at least CF of X is the length of this path where the special input is calculated, right? What I'm saying is this certificate has been achieved at some Y. Y is the special input where the certificate complexity is achieved. This Y has to be there in my deterministic tree. If it is here, I know that the length of this path is more than CF. That means DF is always more than CF. You can think about it, it's not very difficult. Just by the definitions, it will come that DF is more than CF, because everywhere DF, everywhere you have certificates lying. So your depth has to be more than the minimum certificates. Okay, so we know this, and clearly this thing is not true for RF, right? Because in randomized complexity, the trees, the the computational path need not give you a certificate, because we can be incorrect with some error. What about certificate complexity and block sensitivity? Let's fix an input and talk about this. Can you prove this?
Choose the set corresponding to CFX, and that will be a block which for which you can.
That is not
That
correct.
will be a block which will change. Okay, wait.
That is not correct. If you change everything in the certificate, you are saying that your function value need change. That's not correct.
Yeah, got it.
But can you say, okay, so
At least
suppose,
one bit in every block need to be fixed, otherwise we can change the entire block.
very good, yes. So suppose block sensitivity of f at x is achieved by the blocks b1 to bt. Can it happen that the certificate and block b1, the intersection of certificate with b1 is empty? Can it happen? Obviously not, right? Because if the certificate in b1 is empty, that means take the x b1 and f of x should be the same, because I have fixed C certificate, which is completely outside of B1. My function value should be the same, but since it is a block sensitive, that means this value should be unequal. This is a contradiction. That means my certificate has an intersection with each of the blocks. That means size of certificate is more than. Questions about this? Did people get this? C intersection B1, why should be I? Why cannot it be phi? Should I explain it once more?
Yes.
Right. So remember, the block sensitivity, the biggest block sensitivity, let's say it is T. That means I know there are T disjoint blocks such that f of x is not equal to f of x. Correct? This is by the definition of block sensitivity. But if you look at xb1, have I changed any value of the certificate? If C intersection b1 was phi, then I haven't changed anything in the certificate. By the definition of the certificate, f of x should be equal to f of xb1. This is providing a contradiction. C was a certificate at, yeah, sorry. C was a certificate at x. That means if I fix the value of C, you can change anything, my function value will remain same. That is implying this, because B1 intersection C is phi. On the other hand, since B1 is a sensitive block, f of x is not equal to f of x B1. This is a contradiction. That means some variable of B1 should definitely be inside my certificate. That means C contains one element, at least one element from B1, ultimately at least one element from B2, at least one element from BT. That means the size of the certificate is at least T. That means C f of x is greater than BS. This implies C of f is greater than BS of f. Okay. So just these basic results actually give you a nice diagram about all the complexity measures you have studied. You have DF. Today we have looked at certificate complexity, which was less than DF. CF is more than, what did we just prove? CF is more than,
Block sensitivity.
and block sensitivity is more than
Sensitivity.
sensitivity. Now you have RF, you have QF, and you have degree. Sorry, I should not say it like this. What do I know about QF?
Less than
Less
RF.
than RF.
Less than RF. What do I know about approximate degree?
Less than QF.
Less than?
QF.
Less than twice QF. Oh, less than degree.
Less than definitely degree.
And also,
Yeah, so this is kind of slightly weak, right? This is saying that QF is more than, but we understand what it means, right? If some
yeah.
Q of F is omega of approximately. So this is the diagram between the complexity measures. It turns out there is a proof where you can even do this. You can show that R of F is block sensitivity of F. The intuition is that every block should be queried at least, like some 2 by 3 times or something. So then you will get this result. I will not go into the detail of this. In the notes, I have given you a reference where you can see the exact proof of this. But now, we have this figure. So DF is kind of the biggest thing possible. There are many ways we define the combinatorial measures like certificate complexity, block sensitivity, sensitivity. We define randomized complexity, quantum query complexity, we define degree. All of them are kind of have this nice diagram. They are becoming smaller and smaller. But can it happen that my deterministic tree is very big, DF is very big, but block sensitivity is very, very small. DF is n, but the block sensitivity is 1. Can they have exponential separation? Can it happen that DF and sensitivity have exponential separation? What about approximate degree? If you look at this figure, kind of there are two things at the bottom, right? What are the two bottom things? Which are kind of at the bottom, nothing is below them.
And sensitivity and approximate degree.
Approximate degree, right? So what we will see is sensitivity is kind of hard to tackle, but tomorrow we will see that all of these quantities, DF, CF, RF, degree F, QF, actually it just happens that I will be able to bound DF in terms of block sensitivity and bound BSF in terms of degree. The only thing is that now I'm allowed to have a polynomial relation. I can say that DF is less than BSQ. Can it happen that DF is less than degree, approximate degree 4 to the power F? So even if I get a polynomial relation, I'm fine. So what I will show is you remove sensitivity. Everything else is polynomially related. It cannot happen that DF is n and block sensitivity is log n. DF is n and degree, approximate degree is log n. Even log n, it can't even be n to the power 1 by 6 or something. So that is what we will show tomorrow. And that was the state of art for close to 30 years. In all these measures, we knew that everything was polynomially related except sensitivity. Only 2 years back, in a phenomenal result and a very elementary, very nice result, people were able to relate sensitivity to this other jungle of complexity. You can find blogs about it, about this result. Terry Tao, Scott Aronson, all the big names have talked about it. We will see a proof of it next week. That is the plan for next week. First, see, accept sensitivity, how everything is related. Once we have done that, then we will see how sensitivity is related. The sensitivity relation has come out very, very recently. And it is a very nice example of how Boolean functions are special. We will see, we will use the property of Boolean functions intrinsically to show this. That is the plan for tomorrow and next week. Notice that when you talk about partial functions, many of these things do not make sense, right? And for the measures which make sense, there can be exponential differences. For example, we know functions where df and qf are exponentially separated. Df is n to the power half or something, and qf is 1. Such examples are. So for partial functions, things can be very, very. Our job in the remaining time is to show that for total functions, this can't happen. These complexity measures are intrinsically related. That finishes the lecture for today.